Okay. So sorry for Saturday, there was some disturbance and the power cut, everything. We could not finish about our CAN discussion. So if I remember that we talked about this data frame, and then we started discussing about this arbitration field and its importance in priority in arbitration. Okay. So as we discussed that this priority arbitration or this arbitration field is mostly important to identify when multiple nodes in canvas they are connected, which of them will get hold of that bus. That means node 1, node 2, node 3 all are trying to communicate, all are trying to transfer to the canvas. Now who will get the access? That is dependent on the priority of this identifier field. Now, what do we understand by this? This identifier field of CAN is 11 bit. Okay. So when any node is sending the message, this first bit is the start of frame bit. After that, next 11 bit of that message frame, the data frame, need to be checked. Now the bits present in that identifier field decides who will gain the access. Now the decision of priority, I mean to whom you will consider that it is of high priority and which one is of low priority. That is dependent on the dominant and recessive level of the bus or signal level. Now, if you remember our last day's discussion, Saturday's discussion, we talked about that CAN is functionality of CAN is dependent on the differential of voltage. Now, the differential voltage, if it is around 2.5 volt, we consider it as dominant level. And if it is plus minus 12 volt, then it is the recessive level. Now let's consider in a simple term, let's consider this dominant bit. If we think that it is something that means low level, that means 0, and this is 1. Just the concept of CAN, that is the 0 and 1, that is not directly considered as a high voltage or low voltage, not like that. This dominance or recessiveness is determined by these values of differential voltage. Now, here the priority is decided based on 0 dominance. What does it mean? Means whichever node will send early 0 bit, that will gain the dominance. That means just consider this now, these values. This is initial start of frame. That should be always at this low level. Okay. Maybe you can consider that is a dominant bit. After that, these 11 bits, these are the identifier bits. Now, if you follow these identifiers for node 1, node 2 and node 3, these 10, 9, for these cycles, all these 3 bits, they are sending same signal levels, or same, we can say in general term, they are sending same value of bits. 8, 7, same value of bits. 6, same value of bits. So there is no change. So up to this 6th cycle, it is not possible to decide which of them among node 1, node 2 or node 3 will gain the access of CAN. Okay. Now come to this cycle 5. Here you can see in node 1 is at 0 level, node 2 as 1, and node 3 at 0 level. That means that since we consider the zero dominance in CAN communication, that means now node 1 and node 3 will be at high priority state. Whereas node 2 here, since it is sending a signal 1 level, or yes, 1 level in the bus, that means it is losing the competition in terms of priority. Again, come to now the competition is only between node 1 and node 3. Now come to this fourth and third. So for these two cycles, both node 1, if you observe this clock cycles, node 1 and node 3, they are sending same signals. They are in same 1 level. So again, decision cannot be made whether node 1 or node 3 will get the access. Now come to cycle 2. Here, node 3 is sending 0 level signal, whereas node 1 is sending high level signal, 1 signal. So in that case, node 3 is gaining the priority, and the rest of the communication, the bus communication, will be controlled by, now the communication from node 3 will be taken place, and node 1 and node 2, they have to hold their communication. They have to wait for the next coming cycles to send their data frame. Okay, so this is the idea how CAN controls their priority decisions. CAN makes the priority decisions when multiple nodes are communicating through this shared medium. Okay, so this is the typical idea of priority arbitration, and this is the importance of identifier field. Now then, this is the RTR bit that maybe if you remember we have already discussed. This is the remote transmission for remote transmission request. This is a control field. Control field is telling that how much actual data is bytes are actually getting transferred, and based on that, data field will consider, or data field will contain that amount of data bytes. Okay. So this is the basic idea of why this is identified. Maybe these 11-bit fields are the most, we can say, one of the most important bit sequences that should be considered. Okay. This is one type of frame we have considered. That means when the communicating nodes are communicating, they are, first of all, the most important thing is for communication, data communication, they are sending data frame for message transfer. The next one is the next type of frame they can send is, this is the error frame. That means one transmitting node, CAN node, is sending some data frame, and it is expecting that it should be delivered in some particular destination. But in between, the transmitter is actually detecting some error, or the receiver is raising some error signal. So how that error will be communicated from one part of the one CAN node to the other CAN nodes? Because when there's a broadcasting scenario, you are, I think so far you have understood that when any CAN node is trying to communicate to others, basically it is broadcasting the data frame to the medium, and whenever required, based on this identifier field, whoever whichever nodes are the actual taker of that data frame, they are actually accepting, others are rejecting based on the identifier field. Next one is, in this error frame, when any error is actually detected, then that particular node will generate one active error flag. Now, what is the basic structure of this error flag? It will have 6 consecutive dominant bits. I hope now you know that how we are actually going to represent these dominant bits. What will be the voltage level if we have that for that bits, and how to represent that. Now, another error flag is passive error flag, that is considered, that is same with recessive bits and 6 consecutive recessive bits. Now, in this when initially CAN was proposed, this type of 6 consecutive dominant or recessive bits was used to, was allowed. But later on, there was a concept of bit stuffing in CAN. Bit stuffing in CAN. Bit stuffing means, now you think, when you have multiple CAN nodes like this, and they are sending this type of data frames. They are just sending some differential voltage levels and so on. Now, when multiple sequences, consecutive same sequences are getting transferred, that means your signal is like this. A constant straight line, straight voltage level. So with these type of signal transmission, there is a chance that transmitter and receiver, they may lose the chance of synchronization. That means when there is a toggle, let's say if this is a toggle and transmitter and receiver, they both know what is the size, what is this length of this part. But when there is a transition, they can actually check what are the number of bits, and these transitions help the transmitters as well as the receiving nodes both to consider, to be in a sync. But when these type of constant signal is there, that there is a possibility with in case of transmitting these type of constant voltage signals, that transmitter and receiver, they are losing their synchronization. So for that, there is a concept in CAN that is called bit stuffing. That means no consecutive 6 constant bits will be allowed. In between, after 5 consecutive bits, if required, there should be one added some stuffing. That will be some extra bits that is not required, that is not related to actual data, that is not actually representing the actual data, but that is just used only to balance the synchronization between the transmitting node and the receiving node. Okay, so this is one concept, that where consecutive 6 same level bits are not allowed in CAN network. So in case of error frame, but this is a particular frame where these type of 6 consecutive dominant bits are allowed, and that signifies that is the error flag raised from a particular node, signifying that there is some error in the CAN scenario. Okay. So these are the 2 typical types of frames. Those are important to know in CAN, and we will see how this error frame and this error flag specifically present in a CAN, actually they are helping to handle error in CAN. There is another type of frame also, that is overload frame. We will see it later. First, to understand this fault confinement and how these error frame and this error flag, they are actually helping to manage fault or manage error in CAN scenario. Okay. Now, first thing is that why this type of fault confinement, why we are discussing this fault confinement. Now, think about the CAN nodes. The nodes, they are connected with a normal CAN bus. Some error, maybe there was some generation of error, this node A is detecting some error. Maybe that is due to the delay in this or some congestion in this CAN bus. For that congestion, whatever data frame CAN A is sending to maybe to CAN B, maybe this is CAN B, that is not getting accepted. this scan node A is checking that, okay, I'm not receiving any acknowledgement for whatever I have sent. That means there is some error. Then let's raise one error frame, so that all the nodes in the connected to this CAN bus, they will get to know, okay, there is some error. Now, if that happens continuously, you understand that already there is a congestion. For that, we cannot accept any frame. It is proper frames, actual legitimate frames, they are not getting delivered to their destination. Moreover, the scan node A, it is sending again continuously raising error frames. If that is going on, then the situation will never, cannot be improved. There is no scope that if you are already sending multiple error frames on top of some congestion, then there is no possibility that sometime the congestion scenario will get resolved. So in that case, there is some typical technique present in CAN network, that is called this fault confinement network, that if some major fault occurs, there is a technique to how to resolve that. So we can actually model that fault confinement scenario again with this state diagram. So for any node, any CAN node can have, now you understand states and this state transition diagram, so I think it will be easy to understand you this fault confinement scenario. So any node can be represented by three major states. One is either it is error active, either it is error passive, either it is bus off. In general, that means error active means when any node identified that there was some error occurred and it is sending the error frame. Error passive means this node identified that some error occurred. It started sending some error frames, but after some time it stopped. It is detecting error but not doing anything. That means not sending any frame to communicate to the whole network that yes, there is some error. Okay. Now this bus of it means total isolation from that CAN network. That means whenever any CAN node beyond a certain threshold, sending that error frames, that node is getting isolated that from that CAN node. It is not at all receiving, it is not at all sending anything. So that is the state of total isolation, and that is called the bus off state of CAN node. So these three states typically represent and typically help in fault confinement. How? These fault confinement or fault management or error management are managed by using two error counters. Okay. One error counter is received error counter or REC, another is TEC, transmit error counter. That means whenever any transmitter recognizes an error, it increases the TEC count by a certain value. Okay. Again, whenever receiver detects some error, sees an error, it identifies the receiving count by a particular value. Okay. Now, this will go on, because if there is some congestion, if there is no, maybe node A, as we have taken with the example, that node A is sending the frame and it is not continuously getting delivered to node B. That means node A is continuously detecting the error, and it will detect the error, it will send the error frame, and it will increase its transmitter error count, TC value. Now, after a certain threshold, that means if TEC is less than 255 but greater than 127, And REC receiving error counter is greater than 127. These are the values set with some previous calculations. There are some behind calculation depending on the timing requirement and many factors. But just at this point, you should know that these are the values set for these error counters. And when these values, I mean, these error counters go up beyond these particular thresholds, like TEC and REC both are better than 127, then this particular CAN node is moving to error passive state. This is the transition. That means now this state will try to detect whether there is there is a decrease in there is a possibility of solving this error situation or not, but it will not send any error frame. Okay, there will be no transmission from this error passive state of the scan node. Okay, that way if it sometimes check and identify that now this TC is less than 127 and REC is also less than 127. That means there is that indicates minimization of some possible error. Then this node will move from error passive to again error active state. Okay. If that is not the case, that means if the situation is getting worse and this state is again identifying some more errors, and it is identifying this TEC count is getting increased. This TEC is greater than 255. At that point, this node is moving to this bus off state. Bus off state means it is total isolation. This node will not send anything, will not receive anything. So in this way, the advantage is that if there is a congestion to a particular node, let's say this A, this is B. If there is a congestion in receiving on transmitting point of this node, or if this node is faulty, and if it is required some direct restart or some intervention, a technical intervention to make this node proper so that it can again properly transmit and receive the messages and it can work accordingly. So if that is the scenario, that if this node is giving time for that, maybe manual intervention for the technical the determination of why that fall is occurring and why the congestion is occurring, etc. So that is the state that is called bus off state. When the solution was provided or that congestion was removed some other way, maybe by some reset, network reset, or other kind of intervention, with that reset, this burst of state again moves back to error active state. Error active means again it will start the normal transmission and it will check if there is a possibility of error. Again, it will start sharing or sending the error frame to the general network. Okay, so this is the idea. This is how this CAN network or the nodes of the CAN, the way they are designed through this model, that they are self-sufficient to handle the error or a fault beyond a certain point. Okay, so this is the idea of fault confinement and priority arbitration. These are the specific features that makes CAN popular in this embedded domain, because now you understand, right? In embedded scenario, when we are talking about embedded communication, real-time requirement is very high. That means you have some real-time deadline that that CAN network, that message delivery, data frame delivery should be, that need to be met. Now, if that is failed, that is faulty, that means there is no purpose of communication within that CAN network. That's why there should be some mechanism to handle the error to handle fault also within the network itself. And this fault confinement is one example of that. That's why CAN is really popular in embedded domain or in real-time domain. Okay, so is there any question or do you want me to repeat any part? Are you there? Are you listening?
Yes, ma'am, it's clear.
Clear, right? Okay. So this is the idea of the fault confinement, priority arbitration. These three things actually, when you if you now see any other general protocol, you will see these three features. One is that differential voltage consideration, not the typical voltage consideration, but the differential voltage consideration, fault confinement strategy, and this priority arbitration handling in shared medium strategy with arbitration field bits. So these are few typical features that are very important to be considered in CAN. Actually, I will here I have just given the idea, everything. So if you are actually, I will modify the slides. I will add a few, one or two slides here to add the what are the typical values of each and every field. So whatever slide I will upload there, you will get the idea what is the total value of these data frames, what is the total values of this arbitration. I think identifier field, 11 bit. So other than that, control field, what are the total number of bits actually specified for that. So everything will be there. But here just understand that how it is working and what is the philosophy between. So this is another type of, maybe the last type of frame we will discuss here. That is the overload frame. Now this overload frame indicates, see, whenever one thing we have mentioned, that is the error frame. Whenever there is error, the one frame is said to the overall CAN network, yes, there is some error occurred, that is getting notified to all the broadcasted to all the nodes. Another one is, maybe one receiver has sent that to some receiver has detected that one message has came destined to that particular node. Maybe node B has identified that node A that cannot be identified that from whom the message is coming, but the node B has identified that one message has came that it should accept and the process later on. But the node B, there is some possible congestion or the overloading in node B. Now node B has detected that overload and it can communicate to the other nodes that it is overloaded, and that's why there should be some delay that should be maintained by the from the transmitter side, and after that delay some next frame should be sent. Okay, so that is called the overload frame, and that is associated with another flag that is called the overload flag. So this overload flag is again very important to avoid congestion in CAN protocol, and for you can understand, for delay minimization, to request for a gap to a hold to the transmitter side. So these are the mainly three frames that work in the CAN communication. Okay, this is a detailed reference where you can get everything about this whatever we have discussed in the class, and I will modify the slides. I will add one or two more things, like what are the bit sizes, and another thing is not there. I will explain it by my own. That is, if we go back here, yes. Now we see, for this message transfer in CAN communication, maybe we have discussed most of the things. We have now, you know that what we mean by start of frame, why it is required. It is required for synchronization between sender and receiver. Then what is the purpose of this arbitration field? This arbitration field is again for that is basically working as an identifier. So which of the nodes will actually be the taker of that particular field, or what will be the priority, which node will get the priority of this field when multiple nodes are trying to access the shared CAN communication bus. So these are the function of this arbitration field. Next is the control field. Control field, we know that will control number of data bytes we can send in this data field. Data field will actually send the actual message in form of 10, dominant and recessive signals. In that form, it will actually send the data. Next, CRC, I will come to that. That is not there. This is acknowledgement field. Acknowledgement fields that will set high when any receiver is sending the acknowledgement for a particular message that yes, I have received that frame. So that is assures the communication, that assures that is important for assuring the reliable communication, that transmitter is also getting the information, yes, whatever it has sent, it is actually received to the receiver, received by the receiver. And next, end of frame, that is again important for synchronization between sender and receiver. Okay. Now one thing is left. Yes. Yeah.
Ma'am, multiple nodes can receive message from the transmitter. Is it
Yes.
right?
Yes, it is right. Based on the arbitration field, if multiple nodes see that yes, those type of arbitration is important from them, then they can receive it.
So, ma'am, the acknowledge field would also be like that number of bits large,
Yes, that
probably.
number of bits. Acknowledge field is that particular, for that particular arbitration. And see, maybe whenever the sender is sending, it knows how many nodes are actually going to use or are going to accept that message. Okay, so that number of acknowledgement frame, it will actually try to accept. It will actually expect to accept, I should say.
But ma'am, the CAN bus actually never knows, the bus itself never has any information about who all will receive. For example, in fault confinement, we will never be able to know if the receiver is like which exact receiver is creating a problem. Is that right?
That is right. But thing is that not exact receiver, I'm not talking about exact receiver, but what I'm telling, whenever any transmitter is sending any data frame, it has the idea that how many data nodes, how many CAN nodes, for how many CAN nodes that data frame will be useful.
Yes, ma'am.
That is known, right? So
Yes, ma'am.
whenever it is actually receiving for a particular arbitration ID based message, whenever it is receiving acknowledgement, it is accepting, it is expecting that much of acknowledgement message.
Yes, ma'am.
Yeah. So that is the way. Okay. Is it
Yes,
clear?
ma'am. Yes, ma'am.
Okay.
Yes, ma'am.
Okay. Yeah. And in case of fault confinement, it is true that which node is creating the problem, that is not known by the other transmitter or the other CAN nodes. But the node, whoever is actually checking its transmitter, TEC and REC, it is checking whether it is, going beyond a certain threshold or not. Then
Yes,
it
ma'am.
is automatically going to a bus idle state or bus off state.
Yes, ma'am. Yes, ma'am.
Okay. Okay. Clear, right? Okay. Next, one thing we have not discussed, that is this purpose of this CRC field. Okay. This one again, whenever I will upload the slides, I will add one example with it. I'm just giving one idea, the idea why it is important. This CRC field is basically for error checking. CRC, the full form is cyclic redundancy check. So how it works, whenever you will see, whenever you can, you may later on study different other protocols. There also you will see that this error checking in communication can be done by three ways typically. One is parity. Second one is checksum. The third one is CRC. Okay. Now, how they are different? They are different. Checksum a bit different. I'm not going into this, but the parity CRC idea is almost same. That is, whenever you are having some data sets, maybe 1 0 1 0 1 1 something, you are actually computing the parity of it. Okay, and that may be odd parity or maybe even parity. Based on that, that parity is along with your data frame. In your data frame, there will be some location where you can add this error related information. Now, in case of parity, it is quite simple. That means you are just counting the number of ones or counting the number of zeros based on you are setting this number of parity. Or I mean setting whether it is odd parity is 1 or 0, even parity is 1 or 0, like that. Okay. Now what the receiver will do, in the receiving side, whenever the receiver is actually receiving this data frame, it will get some 1010, this type of value in the data frame, and also it will get this parity field. Now this parity field, it will check the parity of the received data frame, and if it matches whatever parity, it will calculate the parity of that received data frame, and it will check whether it is matching, getting matched with the parity, whatever value set in the parity field of your data frame. Okay. Now this parity is very simple. It is quick to compute, but it is having some limitation. The limitation is that whenever you are sending based on the number of counts of 1 or 0, whenever you are sending this 1 or 0, it may happen that what happens when some error occurs and there is a possibility of bit flip of within what possibility of bit flip of whatever you are transmitting. That means you are sending 1 0 1 1 1 0 0 and so on. If due to some effect, due to some overlapping effect, or there are different types of communication interference effect. So based on that, if only one bit is getting flipped to 1 to 0, then with the help of parity, it is easy to identify. But if there are two bits together, it is changing. Then in some cases, maybe I should say in case of multiple bit flips, parity will not work properly. Parity may not work properly. So that's why CRC is a more promising solution. In case of CRC, we define a particular CRC polynomial. Okay, maybe that, and set a few value, maybe some n plus 1 bit value. I should, one second. Wait. We'll just give you the idea of. Okay, after this. You see, here, if you're sending like this, oh, sorry, I should. You are sending a value like this, 101100 or something like this, and you have one CRC polynomial that is of n plus 1 bit. Okay. So with that value, you are basically, you are appending some number of n zeros here with your actual message, actual data bits. And then this whole thing you will be dividing with this CRC polynomial. Okay, CRC polynomial. Then whatever value you are getting, you will add that, you will append that, that is your CRC checker. CRC, you can say remainder maybe. That is you are adding with this your data frame 1011, maybe whatever was there. With that, this CRC value you will This is divided by CRC polynomial. You will add this CRC value with your actual data frame. So this together, the sender will send from sender to receiver. Okay. Now the receiver is receiving this total value, and among them, receiver from this control field, it knows that this much value is actually the actual data bytes. The rest are CRC values. Now the CRC polynomial, again it is known by both the sender and the receiver. Again, that it will apply that CRC polynomial on this value and it will get the remainder. If that is 0, then there is a match and the receiver will get to know that whatever value the transmitter was sent from the transmitter side, the same has been received by this receiver side. Okay, so this is the basic idea how this CRC applied added bits, added the CRC checkers will help the error handling in CAN. So for this, this CRC field is actually given. I will add, when I upload the slide, actually I will add one extra added example with this so that you will understand how this algorithm actually works. But the important thing is that the CRC field, this is this is very important, though this is not actually containing any actual data message bits. Basically, whatever frame size you are considering, you can understand, right? If among them you could have sent a full frame, you could have utilized a full frame only to transmit the data, the required data bits, then of course it would have have been increased your performance. But here these parts adding CRC checkers, that may utilizing some of the bits that could have been used for your actual data transfer. That means actually it is reducing your data rate, the transfer data rate, but still it is important for error checking and error handling. Okay, so this is the basic idea of message transfer in CAN and how CAN works. Okay, there are many more versions. I have just discussed in this because this is a fundamental class, and I have just discussed the basic version of CAN. There are some extensions of CAN FD, and there are things, but basic idea of CAN and CAN communication is like this. Okay, so this is about CAN communication, and I'm going to share one thing with you. I think that is for your self-study. That is, so far whatever we have discussed, that is based on some shared medium, how the communication is taking in the shared medium. But here, this is one document, and I will also share the recorded lecture also to understand for direct communication, what is the protocols present in embedded domain for direct communication. Okay, so that is, you can understand when we have talked about CAN, that is the most complex one, but when the direct communication, that is quite simple. For example, if you can consider, this is one type of communication, UART. This UART communication where this one transmitter and one receiver, they are communicating directly. And for this, from this you can understand how UART works. You can see here the packets, whatever the data streams transmitter is sending from receiver, you can see these are quite simple. Those are just one start bit, one or two stop bits. Again, here you see the parity used for error handling. Because this is direct communication, the possibility of bit flips or bit divergence is lesser, so parity, the simpler algorithm, is okay to communicate. And this is the data frame where the actual data communication is taking place. So this is these type of different communications are there. I will just let you know up to which you have to study. You will get the idea how UART, ITC, I2C, USB, these protocols, a small difference between them due to for typical advantages and disadvantages. So I will share this document as well as a recorded lecture with you, so that you will understand that how typical point-to-point communication, direct link communication can be taken place in embedded scenario. Okay, because this is my last class, so from next class onward, Manipata will take some lectures on sensors. Before that, I want to give you one important concept when we are talking about embedded design. Okay, so for that, uh, okay, for that one idea is that maybe we have not discussed at that point of time. That is, if you remember whatever we have discussed so far, we know if we have some specification. From there, we talked about different types of modeling techniques. Okay. From that modeling technique, we know how to optimize our problem, how to get a better understanding of our specification, and then how to move to the, and after those parts are done, we are moving to the implementation part. Now in implementation part, we talked about that there may be different processes. On that processes, based on our modeling, whatever components we are getting from the models, we will be coding them, we will be representing them by whatever instructions my languages and my underlying processors are supporting. Okay. So now and then we will do the implementation to get our embedded system ready. Okay. But these are typical steps we need to follow for our embedded software design. But here in this last few minutes, I want to discuss few aspects that may affect your design, and that you will see that you have done everything correctly. You have taken the specification, you have chosen your modeling technique properly, you have chosen your processor properly, you know one language, you have coded properly with the instructions. Still, your embedded software is not working properly, and there may be a few reasons that need to be taken care of. The first one is, see, when we are talking about embedded software, one important requirement is, again, the deadline. You have to meet the deadline. Your embedded software should complete the task within the real-time requirement. So if that is so, that means whatever implementation you have done, you are expecting the execution, a completion of a particular execution within a particular time. Okay. But that means you have actually considered all the implementation timing requirement together. But there may be some factors that may affect your modeling technique, implementation technique, and one of them is the interrupts. Now, when we are talking about interrupt means there may be three types of interrupts. One is hardware interrupt, one is software interrupt, one is exception. Hardware interrupt means when some external hardware changes the voltage level of the interrupt request line. That means every processor, maybe if you have worked with any processor, they are having some interrupt line. So that interrupt line is getting request from an external software or getting triggered by a special instruction, and that is the software interrupt coming within. And next, the exception, that is by some faults detected in the internal hardware. So hardware interrupt may be anything that is required to be handled, required to be managed, stopping your normal execution. Okay, that may come from external side, that may come from your some faulty execution or limited execution of your internal executions. But the thing is that you understand now, whenever this interrupt comes, you have to stop your actual execution. That means maybe you are executing some instruction like this. This is the main program. Okay. These are the instructions. Instruction in, maybe you have to execute from instruction in to instruction in plus 4. But this up to instruction in plus 2, after that there is some high priority interrupt that occurred, and for that you have to stop your instruction execution. So this is the step what you will do, that you will save the program status word, then save the return address. And return address means you have to save the address when after the execution of the instruction is interrupt is complete, you have to again come back and you have to continue with the next instruction. That's why it is important to save the return address. And after that, what you have to do, you have to run a routine. Routine means again some set of instructions that you have to execute, that your processor will execute, that will actually execute the complete the steps to handle the interrupt, and then again you will restore your program status word, you will check what is your return address, and you will complete your instruction execution. So that is how instruction interrupts or exceptions are handled. Now, since you want, now with this idea, I think you understand that whenever there is an interrupt, that interrupt is taking considerable amount of your execution time. Maybe if your any high priority task was running and in between some interrupt occurred, that means that interrupt will take some amount of machine cycle, some amount of time, so that your high priority task will halt. So, and the difficult part here is you never know that when that interrupt will come. So this is something like it is the most challenging part to model. So that's why there is whenever we do the timing analysis of any software, you have designed one embedded software, and whenever you are doing the timing analysis, that whether it is meeting the real-time requirement or not, considering the effect of interrupt is very important, but it is also challenging. That's why people generally take some worst case possibility of how many times the interrupt can come, and this way, if the interrupts are coming, what are the instruction executions to handle those interrupts? You can see here, this is the set. This is one main program running where this is you are executing some code, and you are executing them where the timer count is not 0. You can see this while loop. Now this signifies the interrupt handling. That means when this timer count is 0, that means interrupt is triggered, and within that time you have to stop your general execution and you have to execute that interrupt. You have to handle that interrupt. Okay. So that's why it is important to model the interrupt also along with your main programming model. Maybe you can think that they are also some concurrent machines, some interrupt timing requirement. If that you are considering that as a timer, that the timer is counting maybe from 200 to 0, and then when it will stop, it will trigger and raise a request to handle that interrupt. So there are maybe two states. One is idle and one is maybe active state of the interrupt. So in which state it is present, based on that, whether you have to check whether your main program execution, whether it will halt or it will stop. So this is one important factor that will affect, in spite of the fact you have done everything correctly, you have modeled it correctly, you have chosen processor design correctly, you have coded correctly, everything is right. Then also, if you do not consider the effect of interrupt, then that may, the total timing requirement computation may go wrong and that may actually your processor, your design may not achieve that real-time significance. Okay, so this is the how your modeling it is shown. I think you have the idea of how FSM design can take in place. So based on that, they are the two states where one is inactive state of the interrupt and active state of interrupt, and based on the modeling is done. This is one. From there you can get the idea. Maybe that was one question based in your initial discussion, introductory discussion. So this is just to give an idea that in case of watchdog timer, sometimes whatever processors you use, those watchdog timers we use as a normal timer or interrupt generator. But this watchdog timer is basically a monitoring device. So it checks and monitors whether your distant placed cyber-physical system or embedded system, it is working correctly or not. So if you see this diagram, you can see that this watchdog timer, it is checking and it is expecting a restart input within a certain time from your general embedded system. And if it is not receiving, it will send a timeout signal and it will restart your embedded system. So that is the basic idea of watchdog timer. In spite of the fact these watchdog timers we actually use in some cases, basically when it is remotely placed, then only we can feel the actual purpose of this watchdog timer, the responsibility of watchdog timer. Otherwise, this circuit is not properly used, underutilized, and that's why we sometimes use it as interrupt. So get this concept clear. And another, so maybe today time is over. Okay, I will check if I get one extra class or extra schedule, I will discuss it. Okay, so this is another concept of how your writing skill of your program or writing of your software may actually affect the whether your software will be active or not, whether it will be suitable for embedded processor design or not. So that part maybe I will check it out. Okay, is there any questions so far?
No, ma'am.
Okay, so today I think that's all. I will see if I can get one extra at least 20 minutes class, then I will discuss that part. Okay, so thank you for today.